Welcome to this short topic, symmetry. So to understand symmetry, we first need to visit the two types of symmetry, that is line symmetry and rotation symmetry. We're going to start with line symmetry. Okay, so what is line symmetry? So line symmetry is all about this characteristic of shapes. When a shape is cut somewhere, the two parts that are formed as a result of that cutting, they should be mirror images of each other. What does it mean to be mirror images of each other? When you look yourself, when you use a mirror to look at yourself, you're going to see the exact image of how you look, but you're going to be facing each other, but it's going to be the exact shape and size. Okay, so that's what it means. So if you have been given a shape, if you can somehow divide it somewhere to make two shapes, and those two shapes are mirror images of each other, we say this shape has symmetry. Okay, let's take a look at let's say we have this triangle here. So if we put a mirror along this line, okay, so this triangle is going to have a reflection like this. Okay, so if you have been given a complete shape like this, a triangle which is like this, and you can see that if I divide this triangle into two parts, this part and this part, then the parts are going to be mirror images of each other. Then we say this shape has symmetry. And if you can do that once, like here, we say this shape has one line of symmetry. Okay, so let's take a look at some common shapes and the number of symmetry they have. So these ones can be mastered, but there's some shapes where you have to think or imagine. So we've got the isosceles triangle. An isosceles triangle is a triangle with two equal angles or two equal sides. Okay, so this triangle has this angle and this angle are the same, and this side and this side are also the same. So this is an isosceles triangle. So for an isosceles triangle, it only has one line of symmetry here. You see, if we divide it using this line, this part is a mirror image of this, and this part is a mirror image of this. What simply this means is, if you put a mirror here, okay, and if your mirror is facing this side, if you want to see how this side is going to appear on the mirror, what you're going to see is this. Okay, again, if you put a mirror facing this side, the reflection of this one is going to be this. That's what it means. So for an isosceles triangle, you can only divide it once. There's no other way in which you can divide it to get mirror images. The next type of triangle, or the next shape, is equilateral triangle. So for an equilateral triangle, it is a triangle that has all the angles equal and all the sides equal. So this angle, and this angle are all equal, and this side, and this side are all equal. So for an equilateral triangle, it has three lines of symmetry. You can divide it. You can divide it here just like an equilateral triangle. Just like an isosceles triangle. You can also divide it here. Okay. So if you draw a line here, this side is going to be the same as this side. Again, if you draw a line here, this side is going to be the same as this side. I'm going to do illustrations for you just to be able to imagine the symmetry, but we're going to do that later after we look at rotation symmetry. So for a rectangle, for a rectangle, it has two lines of symmetry. It can be divided like this and like this. Then for a square, we have four lines of symmetry. You can divide it like a rectangle. Then you can also divide it using the diagonals and the diagonals. Those who don't know the difference between a rectangle and a square is that a rectangle has these two sides which go top to bottom, and these two sides which go left, right, different. Okay, the length, they have different lengths. So the length of this and this are the same, but they're not the same as the length of this and this. In short, the two opposite sides have the same length. So these have the same length and these have the same length, but this and this don't have the same length. But for a square, all the sides have the same length. So this, and this have the same length. So that's the difference between rectangle and square. Another interesting shape is a circle. So for a circle, it has what we say infinity or uncountable number of lines of symmetry. It has infinity lines of symmetry or uncountable number. Yes, uncountable lines of symmetry. Okay, so meaning that for a circle, you let me just get a pen to illustrate. So for a circle, let's say we draw lines such that they are passing on the center. Okay, so we can draw this line, not accurate though. This side is going to look the same as this side. We can draw this line. The top side is going to look the same as this side. We can draw this line. We can draw this line. No matter how many lines you're going to be drawing, the sides are going to be appearing to be the same. Okay. Next, we take a look at rotation symmetry. So rotation symmetry is the symmetry in which a shape can be turned about a fixed point and fit exactly onto itself. You get a shape, you turn it. As you are turning it, at some point, it looks exactly the way it was at first. That's rotation symmetry. Okay? So there is what is called the order of rotation symmetry, which is just the number of times that a shape can be turned to fit exactly onto itself within 360 degrees. Okay, so what this simply means is you get a shape, then as you are turning it, okay, the number of times that it's going to, as you are turning it, it's going to appear like the way it was originally. That's what is called order of rotation symmetry. However, when you're turning it, when it reaches the same position as it was before, you end there. So when you turn it such that it reaches the same position it was before, we say it has turned for 360 degrees. So we say that it has turned 360 degrees. So every shape has an order of rotation symmetry of at least 1. So for line symmetry, you can have a shape that has no symmetry. Okay, but for rotation symmetry, every shape has a rotation symmetry of at least 1. Okay, so let's say we have this smiley face here. So let's turn this, we see what we mean by rotation symmetry. So if we turn it about the center, okay, about the center here, okay, so if we turn it about the center, when you're describing rotation symmetry, you have to describe the order of rotation symmetry and also what is called the angle of symmetry. And at times, the point at which on which you are turning it, okay. So anyway, we're going to take a look at examples. So if we turn it about here, like if we rotate it, not rotate, anyway, even rotate. If you rotate it about this point, the center, let's see what's going to happen. So it's turning, it's turning, it's turning, it's turning, it's turning. So now it's looking the way it's looking exactly the way it was looking at first. Okay, this, remember, is the original position. So if you turn something, it's not looking the way it was at first, till you get the original position. It means you have turned for 360 degrees, and still that shape has a rotation symmetry of 1. Okay, you get something, you turn it, you turn it, you turn it, you go to the original position. Okay, that thing has rotation symmetry of order 1. Okay, that's how it is. We're going to look at more interesting shapes for us to appreciate. So another term that we need to know on rotation symmetry is angle of rotation, which is given by 360 degrees divided by order of rotation symmetry. So we first need to know the order of rotation symmetry, then you divide 360 by that order of rotation symmetry. So let's do some illustration on rotation symmetry so that we train ourselves how to imagine something rotating. So let's say we have this shape, okay? So when they ask you to find the number of rotations, the order of rotation symmetry for this shape. So this is an equilateral triangle, meaning that this angle and this angle are equal. Remember, on lines of symmetry, we said this one has one line of symmetry. There's some sort of connection between line of symmetry and order of rotation symmetry. Something that has one line of symmetry, the chances that it might have an order of rotation symmetry equal to 1 are high. Okay, so let's say we rotate this. We're going to rotate it within 360 degrees. In simple terms, what it means is when you're rotating it, when you reach the same position as it was before, you stop. That's what it means to rotate it in 360 degrees. So let's rotate this one. So as we're rotating, you can see it doesn't look anything like the way it was before. So I've just stopped here. It's still not looking the same. It looks the same, but it is upside down. So if we continue doing that, it's rotating about this point. So we're going to get the shape. But again, we've regained. This is like where we started from, and that's when it is looking the same way it was at first. So here we say this shape has an order of rotation symmetry of 1. Okay, and its angle of rotation is 360 divided by 1, which is just 360. Okay, let's take a look at another shape. So this shape is an equilateral triangle. The 3 angles are equal and the 3 sides are equal. So I've put these letters so that we are able to see which corner is which. As we are rotating, we want to stop when the A is on top, the B is on the right, and the C is on the left. When we reach such an arrangement, then it means we have finished rotating. We have regained the original position. Okay, but as we rotate it, we're going to be slower as compared to this one. We're going to see that it will be looking exactly as we're going to be stopping when it looks exactly as it is now. The A and the B and the C are not part of the shape. They're just there to help us identify the corners, the various angles. So if we start, okay. So you have seen it looks exact as it did before. Okay, don't mind the A, the B, and the C. Okay, they're just there to show us the corners. So this corner A at first was here, but now it has gone here. So here we count it as 1. Okay, so keep on rotating. Okay, so here it looks exact as it was again before. Okay, so as you can see, A initially was here. In the first count it was here, in the second count it is here. So we count this as 2. So we continue. So you can see A is going back to where it was till we are here. Okay, so this is the way it was at first. Okay, so we stop here, but even this we count, so it's 3. So this shape has a rotation symmetry of order 3. The angle of rotation, you do 360 divided by 3, which is going to be 120 degrees. Let's take a look at another shape which is not even common, some random shape. What about this one? Okay, so now I want to put letters. You need in an exam they won't be like this kind of animation where it's rotating and you're able to see. You have to think. Okay, so this one we have to picture it in our mind. So just pause the video and think. Ask yourself how many lines of symmetry. Okay, then after that continue the video. You see how many lines of symmetry it has through the animation that I'm going to do. So I'll give 2 seconds for you to do the pausing. All right, so I'm assuming by now you have done the calculations and you have your answer. So let's rotate it together. So if we rotate this, it's not looking the same. No, it's not looking the same as it was before. No, it doesn't look the same as it was before. now it looks the same as it was before. Okay, and this is its original position, remember? So we can say this one has a rotation symmetry of order 1, and its angle of rotation is 360 divided by 1, which is just 360. When we come to lines of symmetry, this has no line of symmetry. There is no line which you can cut here so that one side is symmetrical or is a mirror reflection of the other one. Even if you cut here, no, it can't be. Okay, the other way to view symmetry in terms of line of symmetry is when you choose a line, when you fold the two parts, are they going to fit exactly into each other? Okay, so if you fold it here, is this part going to fit exactly into this one? No. But if you look at this one, if you fold it here, this part is going to fit into this one. If you fold it here, okay, so this part is going to fit into this one. Okay, we conclude this topic by now looking at what matters, the summary of everything on rotation symmetry, describing rotation symmetry. To describe the rotation symmetry, we state the order and the angle of rotation. So you need to state the order of rotation symmetry and the angle. So example, describe the rotation symmetry of the square below. So this square below, let me get a pen. So if you get a pen here, this shape, you can divide it like this. So when you do this, the left and the right side are going to be symmetrical, or you can fold such that they fit into each other. You can also divide it like this, not perfectly drawn, but the top and the bottom, they can fit into each other. You can also do the diagonal like this, okay, and it like this. Okay, not perfect. Yeah, I'm using a computer, so it's not perfect. Okay. So here's the answer. I've added the letters to present the corners, okay, so that we are able to know which corner is which. Otherwise, it can get confusing at times. Okay, so when we are rotating it, when we reach a point where the A is going to be here, the B here, the C here, the D here, we'll stop. But we'll be counting the number of times the shape appears the same way as it is now. Okay, so these letters are just for us to identify the corners. So if we start rotating, we can see the shape appears the same as it was before. Okay, so we count this as 1, 2, 3, 4. As you can see now, A is where it was before, B is where it was before, C and D. So this shape has a rotation symmetry of order 4. So we write our answer as the shape has a rotation symmetry of order 4. Then we calculate the angle of rotation. 360 divided by 4, it will give us 90. And then we say at an angle of 90 degrees. So this marks the end of this topic. The key to this topic is, of course, to look at more shapes and come up with their lines of symmetry and, of course, their rotation symmetry. You'll be able to find the topic easier. Happy solving.